So following on from one of the things that was mentioned there, you've gathered all this data and then you've maybe got to do some correction for us and so on. Leading on to this particular one, Dr. Tingying Peng has been doing a lot of work, I think mostly here in optical microscopy, but it'd be really interesting to see how you see that playing out. So over to you.
Okay, thank you. Thank you, Paul, for this nice introduction. And of course, I also learned a lot from Anna. I mean, sometimes in our medical image analysis conference, I saw this EM challenge, how to do the segmentations. Even I myself, I haven't worked on that data yet, but it's also an exciting field. So a short introduction of myself. So I'm Tingying. I'm a young investigator, group leader at Helmholtz AI. And it's a pleasure to be here for this life science field day and present my research, AI in microscopy. So how we use AI method to go beyond the limit of hardware. So the mission of my group basically is developing AI method for quantitative microscope image analysis. So we'll work on different modalities, including the bright field, fluorescence. So those are mostly 2D, and we also work on 3D, which is a light sheet, which I'm going to focus on. We also work on electrotomography, so which is a bit different from the EM. We haven't worked on EM yet because you heard from Anna, there is only 8 groups who have these machines. Unfortunately, none of our collaborators have these machines yet. So a few examples how we use AI. So one thing we work on is computational pathology. So those are the histopathology slides, which use in clinical settings for cancer diagnosis. So one problem we come up with is this battery effect. So if you heard from Fabian, in the morning, he also talked about battery effect. So the data from different institutes, they tend to look differently. That's exactly the same case for us. So the image from different hospitals, and the data have different colors. That's a problem for AI algorithm, because imagine if you train your algorithm on one hospital, it may not work directly on the other hospital. So therefore, we developed some method which augment this color augmentation or color variation during the model training. So our trained model will be resistant to this color variation, so can be used directly for the data of the other hospital. Another issue we are facing in the medical imaging in general is we have limited amount of annotations. So different from Google's, they work on the natural images, they can get a lot of annotation, use crowdsourcing. We actually need a medical expert to annotate the data. And they are working for patients, they don't have time for us, or so much time for us. So therefore, we actually need a lot of kind of self-supervised learning or unsupervised learning to how to deal with the image processing without the labels. Therefore, we also did a bit of research there. So that basic idea is we have basically 2 augmented versions of the same image. They should be embedded close in the network, where the 2 different images, they should be apart from each other. Through this way, we can actually start training our algorithm. Another solution for that, this limited annotation, is we do have the patient information. So we have the patient diagnosis. We know which patient have cancer, which patient do not have cancer, or what kind of cancer they have. Therefore, we can formulate something called multi-instance learning. So we don't get in the annotation for every imaging patch, because our histopathology image is huge. Usually we break it into patch to fit into the neural network. So we don't have the annotation for each patch, but we do have patch of the whole slide. So which is back. And we can use a transformer to link the information from the patch to the back, and then to do the prediction. So the major topic of what I want to talk today is this how we use AI to closely work with the hardware to improve the microscope imaging quality itself. Here I show an example of this light sheet microscope. So currently we are cooperating with Professor Jan Hauske. So he's a Humboldt professor in University of Göttingen, and he is also the co-inventor of this light sheet microscope. So here a short survey: who knows the imaging principle of light sheet? Nice. So for those who are not familiar, I can do a short introduction. So for light sheet microscope, basically it's characterized by this orthogonal illumination detection path. So it's illuminated from the side. So only a very thin tissue slice get illuminated, and they are getting the signal to the detector. So the tissues above it or the tissues below it, they are not illuminated. So that's very nice because that can reduce the phantom bleaching and therefore reduce the phantom toxicity. And as compared to the confocal microscope, so you only have one single layer which is in focus, but the tissue above and below, they are also illuminated. But because their light are going to reject use this pinhole, nevertheless, they are still illuminated. So that will cause phantom bleaching. So that's one advantage of light sheet. Another advantage, or maybe the more important one, is they actually illuminate one thin light sheet at one go. So for confocal, you do this laser beam. So you do this like scanning process. So it's a bit like the single beam electron microscope, which Anna talked about before. So you focus one point and then you get one signal, and you focus another point and get another signal. And that's slow. And this is quicker because you do the one sheet at one go and getting all the signal from that sheet. So this allows ultra-fast imaging for the living organs, such as this amazing beating Zimba fish heart from Yan's lab. However, we know nothing is perfect. So there is, if you take a close look at your image, you can actually find there is still some problems. One problem is this light absorption due to the structure, such as this. I think this is also fish because that's the eye, and somehow the eye actually absorbs light a lot, and that causes your illumination. So the tissues behind it, they are not getting illuminated. So of course they are not reflect the signal. So that's actually close shadow. And in many specimens, actually the tissues, like the distribution, will be quite heterogeneous. So you get a lot of fine lines in your light sheet microscope. So that's which is called stripe. So deal with these two problems. So we have a very bright student, Liu Yu, who worked on this problem for like around 1 year, a bit more than 1 year. The first algorithm she come out is to get rid of the stripes. Well, she used a graph neural network on the Fourier space. So why Fourier space, not on the imaging space? Is because she found out the stripes are very global, like you are everywhere in the imaging space. Then this is very hard to remove in the imaging space. However, if you turn the image into the Fourier space, and there is a very there is one stripe basically along this x-axis that's corresponding to the corruption to the stripes in the imaging space. So it's might be easier to deal with it on the Fourier space. Therefore, so her algorithm works like she used the corrupted volume, project that into the Fourier space, and then to detect which part is corrupted by the stripes. And then she formulate a graph neural network on a circle in the Fourier space, use the non-corrupted coefficient to predict the coefficient in the corrupted region with using this graph neural network. And she also added some Hessian constraints and to make sure the reconstructed image are continuous and the structure are not distorted. And this works quite nice in practice. So if she simulates the stripes to the images, and you can get some quantitative evaluation, and this also works nicely on the real images. So actually we look for the literatures, we find out there is some similar problem in this scanning electron microscope. I asked Anna briefly before the talk, and she said it's due to the cutting, but maybe nowadays the cutting is better, so you have less problem of this kind. So this is the last slide. So besides the light sheet, as I said, we work on all kinds of images. We also work on illumination correction. So that's also called shading correction. That's because of the uneven illumination of your light, and you get this grace in your stitched image, and we can get rid of the grace, and you get a seamless stitching And last year we got funding from Chan Zuxberg. We rewrite the basic into a Napari plugin, and we want to write another paper for that. And we also work on image deconvolution, so basically make the blur image into a sharp image. That's we have collaboration with Dr. Yan Hoskin in Germany. So he has this very nice underwater light microscope settings. Because he used a very special lens, which called electric tunable lens. So this lens can make your animal where it is, like regardless of the Z position, it's always show up in your final image. So through this lens, he can capture like 20 to 15 times more planktons than a normal lens. However, the cost is the image looks very blurry because a lot of these sets they are out of focus. So we developed a method to do the convolution and make it sharp. We also do electron tomography, which detect the membranes. Actually, here we're cooperating with Marian locally in the HPC in Helmholtz. That's the end, and I'm happy to take any questions.
Thank you very much. Thank you very much. Have we got any questions from the floor or online? I had one particular one while we think about that. I noticed, I guess the interesting question is whether each individual instrument has its own set of artifacts that you have to correct for. Mm-hmm. Is that something that means you can use the same model or foundation model, or have you got to retrain it with a different GNN?
Okay.
For each instrument?
That's a very good question. So currently for our GNN, for particular data settings, so we are doing basically the training is, we need to train on, for each volume, we train the network and test on the same network because we don't need the labels. So that's not a problem because our GNN is more self-supervised. Another question is, we also ask Yan, is it only your light sheet have these stripes and another light sheet do not have stripes? And I have to admit, some size my light sheet I don't see the stripes because they use a different algorithm, different the hardware settings. Yan's microscope have these stripes, but Ali took's microscope also have these stripes. So because it's tissue absorption, so it's kind of really common, let's say.
Well, thank you very much. It's really very interesting, lots of fascinating graphics and so on. But I think for me, the fact that it shows how you can get more information from just the raw data is really great.